All right, here we go. Okay, let me pull this out. Small. Should have done this already, sorry. Put out. Put it over here. Okay. And present my full screen. Share. Okay, so we're going to go over 17.1 notes. I'm just going to go through the parts, and if you guys have questions, you can speak up, or you can just put them in the chat and we'll come back to them. Okay, so chapter 17 is on kinetics, and kinetics is related to the rate of the reaction. So some things happen really fast, like combustion, and some things happen really slow. And the best example is rusting of iron. So it takes a long time for iron to rust, but it's really fast if you're going to burn alcohol or like some pine needles or something. Okay. And a mechanism is the step-by-step sequence. So some reactions, it's one step, A bumps into B, they stick together, they make a product, and it's done. That would be a one-step reaction. But most things, a lot of things, have several steps. So A has to bump into B, they have to bond, and then if there's another reactant, it might need to collide with one of them and then break and make new bonds to form your final product. So if it happens in steps, like step 1, step 2, step 3, that's called a mechanism. And then intermediates, right here, intermediates are something that is made. So let's say it's made in step 1. If that A has to bump into B and stick together and it forms AB, but then AB is part of the next step and it breaks apart again, then AB would be an intermediate. So it appears in the product side, but also in the reactant side, so it cancels out basically. Okay, and our example is this carbon, which would be like charcoal, reacts with oxygen and makes carbon dioxide in the first step. That carbon dioxide then splits apart into carbon monoxide and oxygen gas. So if the overall reaction, excuse me, is it's going to be this carbon reacts with oxygen and makes carbon monoxide. The carbon dioxide, see how it's on the right side of the arrow and the left, it cancels out. That carbon dioxide is an intermediate. Okay, so the net equation is kind of like in math, if you have multiple lines of a problem, you're going to add up everything, and your net is like the total that you'd get at the end after everything cancels out. Okay, so the net equation for this two-step mechanism is going to be carbon, because carbon didn't cancel, so this came down here. I'm going to put that solid in there. So this should actually look like that. Okay, and this one oxygen in these, sometimes it's okay. It's like in balancing. Sometimes it's okay to leave a fraction because you can have a half of a mole. You can't have half of an oxygen atom or molecule, but you can have half of a mole of them. So this 1/2 is all right to keep down here. If you have 1 on the left and half on the right, this is going to cancel half of this, and so you'll have half of O2 gas. Okay, and if that really bugged you at the end, you can double everything to get rid of that. I'm going to put the gaseous state in there. And then this right here canceled half of these out, so we already have our reactants. The carbon dioxide right there. Let's see, where is my strike through? No. Okay, that's going to take too long. The carbon dioxide formed and then used up is our intermediate, so it's not in the net. And this carbon monoxide gas is left over. Okay. That is what's left. So this is our net equation right there. Okay. All right. And CO2 was our intermediate. There are examples in your book on page 562, so you guys can look at those reactions involving hydrogen and iodine. Example 3, I have it right here, so we can look at example 3. And this is a really long reaction where we have 3 steps going on. The carbon combines with the oxygen to make 5 carbon dioxides, and then you have to have the hydrogen reacting with oxygen to make the waters, and then the carbon dioxide and the water comes together to make this guy, which is pentane, and it releases oxygen at the same time. So there's 2 ways to do that net equation. One is to like cancel them out and then write the net after you've crossed stuff off. So for example, I could take this right here and I'm going to highlight it. I can cross it off with this same amount on this left side. So I can just cancel those and then not put them in the net. Or what I did here is I took everything on the left side of the arrow. So this 5C, the 5O2, and the 3O2, I combined them. It's like having 5x squared and 3x squared. You can put them together. So I got 8O2. I have my 6 hydrogens right here, the 5 carbon dioxides, and the 6 waters. And then I added up everything on the right side of the arrows and put them over here on this side. And now it's kind of easier to see that this oxygen on the left and this oxygen on the right cancels. This carbon dioxide on the right and this carbon dioxide on the left cancels, and then the water, the 6 waters and the 6 waters cancel. So we have a lot of intermediates with this one. These are all the intermediates. And the net is just 5 carbons plus 6 hydrogens makes pentane. Okay, so this is our net once you've canceled all the intermediates out. Okay, a homogeneous reaction is when all the reactants and the products exist in a single state or phase. So they're all gases, they're all aqueous, or they're all liquids would be examples of homogeneous reactions. So this one would not be a homogeneous reaction because I see there's solids, there's gases, and there's liquids. There's all of them. So that one's not. Neither is that one. This one is not. But if we did H2 plus O2 makes H2O, that would be homogeneous, a homogeneous reaction. Okay, do you have any questions? Any questions so far? I don't see anything in the chat. Okay. All right, so collision theory, there's 3 really important things. And we've talked about this already here and there, but we didn't write it out yet. So in order to react, it's very similar to dissolving. So the dissolving process we talked about is very similar. They have to collide. If they never bump into each other, then it's never going to react. Okay, so number 1, they have to collide. Number 2, they have to have the right orientation. So picture if the molecule looks like this, and in order to react, they have to bump into each other this way. This will not cause a reaction. This will not cause a reaction. Only when they collide properly will it react. Okay, and then the last thing is they have to have sufficient kinetic energy. So in order for them to actually react, the electron repulsion has to be enough that they can kind of like overlap their electrons. So the electrons, if it was moving really slow, they repel each other, and it's just going to repel, and they kind of like bounce off each other without reacting. But if it's enough energy, they overlap a little bit, and now the electrons on this guy are attracted to the nucleus of this guy. So they overlap and they bond. Okay, so they have to have enough kinetic energy. That energy that we talked about, you're kind of like breaking the bonds that were here and forming a new bond over here. That energy is called activation energy. Okay, so our example is you have hydrogen and oxygen. This is gas. These are all gases. So this is a homogeneous reaction. Forms water and gives off 285 kilojoules of energy. Delta G is something that was in the last section, but we usually barely cover it in honors chemistry. We don't talk about it until we get to AP chemistry usually. So what it means is if delta G is negative, it's a spontaneous reaction or a favorable reaction. So that means that it happens all on its own. Okay, and it's called Gibbs free energy, this delta G. Reaction above, hydrogen, oxygen. Gibbs free energy is negative. So it's saying that this should happen spontaneously, all on its own. And when it does, it's going to give off this much energy. But if you put hydrogen and oxygen together in a balloon, nothing happens. Okay, it's not until, you guys remember the Hindenburg, the big blimp? They filled it with hydrogen because it floated. It was lighter than air, like helium is. But the second there was one tiny little spark, it gives enough energy to start that reaction. Okay, it's the activation energy. And then that released 285 kilojoules, which was enough to start the next reaction. And it's a chain reaction. It just built and the whole thing explodes. Okay. So why does it need that tiny spark? Because the H2 and the O2 are pretty stable and happy on their own. It's not until you give them enough energy that bonds start breaking that then they start to react. Okay, you have to have enough energy to overcome the electron repulsion and to break the bonds, which is endothermic. Anytime you pull two atoms apart, you put in energy. That's endothermic. And when you make a new bond, every time it gives off energy. So if you put these two together, think of like magnets. If I had two very strong magnets here, all I would have to do is let go. And they're going to create energy. They're going to give off kinetic energy. And when they collide, you hear sound waves coming out. So there's energy. So anytime you make a bond, you give off energy. And when you break a bond apart, you put in energy. Okay, that is probably the most important thing in the whole chapter. So I'm going to highlight it. Let's highlight it blue. Okay, super duper important. You have to add a little bit to get the reaction started. That's activation energy. And then the activated complex is this weird thing that you get when you start the reaction. So you're breaking old bonds, but at the same time, things are overlapping and you're starting to make new bonds. So you have this weird intermediate kind of, it's not intermediate, it's activated. You have this weird complex thing that's high in energy because it's not stable, where old bonds are breaking and new bonds are forming. It's basically like a lump of atoms that are not stable yet because they have too many electrons or too few electrons. So it's very high in energy. Okay, and then you guys look at these practice problems from your book. The answers are usually in the back of your book, so you can look up the answers to those. Okay, look at these two. Oh, these are the ones in your book. So looking at these, what are the intermediates? You guys can fill in the blank here with what are the intermediates of the two-step mechanism. And notice this is the exact same reactant and product actually. So we can write the net equation and then see if the intermediates are the same for the three-step mechanism. And in your book, this scenario is given that they don't know which one is the correct one. They would have to study the intermediates to figure out which one's the right mechanism for the reaction. So this is one possibility, and this is another possibility that they just wanted you to kind of recognize net equation and intermediates and see if you can do those. Okay? All right, that was pretty fast. I was going to draw some things over here, so let's come over here. I can draw some energy diagrams. So let's do an endothermic reaction. Okay, endothermic means you start down here, you put in a lot of energy and you get a little bit back. So my reactants would be here, my products would be here, and you have to put in this much energy to start the reaction. This is my activation energy. So the reaction is going from, whoops, okay. Let's say there's like a boulder down here. The reaction of this is taking that boulder and getting it to the product side. So you have to put in a ton of energy to get the ball literally rolling. And then once you get it up here, this is high energy. It's not stable. Okay, it's likely to go one way or the other. This is our activated complex. And then if it rolls down and comes down here, the reaction is over. And it releases a little bit of energy, but you had to put in a whole bunch. So overall, it's endothermic. Okay, and remember that stability has to do with the energy, and low energy equals more stable. So since the reactant side of this reaction is more stable, the products are less stable, it's not a very likely reaction to happen. It can happen, like we can add energy and get it to react, but it's not likely to be spontaneous. Okay? All right. I'm going to cover exothermic another time. Do you guys have last minute questions? That was a really short lesson. Any questions? Oh, wait a minute. No? Okay, I'm going to stop recording. That way, if you want to ask off record. No questions.